Greetings, Kerbonauts! This is Kerbal Space Program. I'm Bob Fitch, and this is a tutorial on how to optimize your fuel. So I have sitting here in front of me a satellite, which I would like to send, well, somewhere. Let's say, for example, I would like to send it to Minmus or something, and have it orbiting around Minmus. Well, the first thing I need to know is how much fuel I need to go to each of those places. I am going to show you how I figure out how much fuel I need, how I know how much I actually have, and how I can calculate that using either instruments in the game or using actual math. Let's begin with knowing how much fuel it takes to go to different places. So what you're looking at right here is what's called a delta V cheat sheet. This is something you can use to add up the numbers in between where you are and where you want to go to find out how much delta V it needs to go between those two places. Delta V is just a shorthand way of saying the amount of fuel needed in order to change my speed from one speed to another that allows me to transition from one place to another. So just getting from Kerbin to Minmus, we need to add up these numbers that go along this line in between Kerbin and the point that begins at Minmus. That's how much it's going to take to get there. That's not how much it's going to take to actually stop and make an orbit around Minmus. But at least at this point, if we have this, we'd be flying by in an encounter. Now, if I'm using Ferrum Aerospace, which I am, then I actually have to use this amount, because it's easier to get into orbit around Kerbin when the air is being modeled accurately like it is in Ferrum Aerospace. Also, if your target is on an inclined orbit, you might need to make an inclination change, and so you need to take into account the worst case scenario, and this is the worst case scenario for going from an equatorial orbit to Minmus in its inclined orbit. Finally, if we add it all up, we see it takes 4670 in our launch vehicle to get us from Kerbin to Minmus. Once we're there, the satellite needs 90 in order to be able to actually capture an orbit, which just means it's going to have a fairly low periapsis, but probably a very high apoapsis. We would need 70 more to bring that apoapsis down to a nice circular orbit of 6 kilometers, and an additional 180 if we wanted to actually land on Minmus. If you are trying to land someplace and take off and go back again, you need to reverse all the numbers. So going from Minmus, it would take 180 to take off into a low orbit, and then another 70 plus 90 to get back to an intercept with Kerbin, in which case you see those red arrows, those represent directions where you can air brake. Once you've reached a red arrow, you can actually make an intercept with your planet at an altitude that will allow you to do an aerobraking maneuver which will capture the planet without needing to spend all the delta V on the lines in between wherever it is you are there and wherever it is you're going, like in this case going from that point where it says Minmus transfer all the way back down to Kerbin itself. Let's say that my satellite wants to make a low orbit around Minmus and just stay there. Well, in that case, I only need 160, which is the 90 plus 70, in order to do a capture and an orbit transfer down to the low orbit. Looking back at the satellite I've made, I can see right here, because I'm using MechJeb to give me a delta V readout, that this satellite right now only has 94 meters per second delta V, and we know we need to have 160 if we want to capture a low orbit. So let's put an additional amount of fuel in here. There, now we have 184, which should be plenty in order to capture the low orbit. So that's the first step that I work on. I always start from the top where I have the smallest payload I can possibly manage, and I try to optimize what I have right there. In this particular case, I was looking for aesthetics. I didn't want to go with the regular fuel tanks. I wanted to have some of these little fuel tanks on the side just because I think they look cool. And so I didn't use my mathematical way of doing that calculation. I just look up here and I see, oh, 184, I need 160, so now we have enough fuel, and I don't worry about that. But let's say that we're now going to try to use the mathematical or the trial and what I call the trial and error method. There's two different ways. If you would like to see the trial and error method, then click this link. It'll skip you ahead in the video past the math section. Right now I'm going to talk about the math of how I actually figure this out if I don't want to use something like MechJeb or Kerbal Engineer. The exact amount of fuel that we need to put on our rocket, and I'm going to have the answer try to come out in a mass fuel side of fuel tank, which means I'm going to take into account the fuel and the tank itself, means that we need to start by looking at the formula here that shows the delta V that a rocket has. dV represents delta V in this. So the delta V is going to be equal to the natural log of the mass of your rocket with fuel, which is wet mass, or W, divided by the mass with no fuel, which is dry, or D. We're going to multiply that times the ISP of the engine and then times gravity. ISP represents the efficiency of the engine, and you can see that in a value like this on the rocket engine when you look in Kerbal Space Program. G is 9.81 and is relative to Kerbin's gravity because the ISP was originally calculated using Kerbin's gravity. And that means in order to get that back out again, we have to multiply by 9.81 again. We're trying to isolate the mass, so next we need to divide the dV by the ISP of the engine in G, which gets us the natural log of wet divided by dry. Then we can use the natural log rule that lets us remove that and put the other as an exponent to E, which I'm going to say is equal to X. I'm doing that because I'm going to use X later in here for 2 points in this formula at the very end. To find X, we need to look at the payload, which I'm going to represent as the dry mass of the payload, which is just a little d. We're going to add to that the mass of the fuel itself as part of the wet mass, and then in the dry mass, we're going to have to add the mass of the fuel tank, which is the fuel divided by 9 in KSP. Finally, we isolate F, meaning the fuel tank and fuel that we want to add, and we get that equal to the dry mass of whatever it is the payload that we're trying to lift, or the stage ahead of it where we're not going to be able to use any of its fuel. We multiply that by x minus 1, and that is all over 1 plus x over 9. Back here in the vehicle assembly building, let's say that I'm really optimistic, and I think that there's a chance that I can get this up on a 1.25 meter rocket. So I need to know the actual mass of everything that's dry. And if we look over here, we can see that it's just about 6 tons. I have added a fairing around the satellite, some fins that I expect to be at the bottom, a gyroscope that I expect to be right there, and I'm optimistically hoping that maybe this engine will get me there. So I put that on as well, just so that I can do the calculation of the mass. So now we know 5.962 tons. We're going to take that into the formula that I just had and the amount of delta V that I need to go from Kerbin to Minmus, and let's see what the tonnage is of the fuel and tanks that we need to add to get us there. With that engine I'm using, it has a 355 ISP in a vacuum, so I'm going to use that for this calculation, and you can see that what that means is it comes out to 29.26 tons of fuel tank and fuel. Adding that to the payload mass, we now have 35.22 tons. And my rule of thumb is if I multiply that times 18, that gives me roughly the thrust of the engine that I want. Now, looking back here at the actual engine's thrust, it says 350. So that is not anywhere near what I'm actually going to want to try to use for the rocket once I put that amount of fuel on there. Not to mention that efficiency was 355 for a vacuum, but at the very beginning of the launch, you're actually using this at sea level value of 320 in this case, and it will quickly rise up to be 355. And so most of your trip will be at the 355, but there's that little bit of inefficiency down close to sea level, and you need to account for that with an extra 100 or 200 delta V. Knowing that that isn't going to be good enough, I'm actually going to switch to a larger engine, and a larger engine is going to mean a larger fairing. So we're going to swap this out. All right, there is our new mass value that we need to enter into the formula to find out how much we would have to lift this as our total dry. And there it is, a fuel tank mass of 43.73 tons, which brings the wet mass up to 52.64. Times 18 means we need a 948 thrust engine, and that's not what that one was. So I'm going to go up one more engine. That puts me at 53.55 tons of fuel, 64 wet mass, and 1160 for a thrust on the engine. Looking back here, you can see that the thrust on this engine is 1400, so that will be enough. Now I just have to figure out how to put that amount of fuel on there and what combination of tanks. And here it is now, finally, with the fuel added on. I have put the fins down here, the engine, some lights, and just to prove this can actually do what I say it can do, you can see I have a couple extra 100 delta V to account for being in the lower atmosphere. I'm going to go and send it to Minmus. Because this is Ferrum Aerospace that I'm using, you're going to see me do my gravity turn very, very early because there's less atmosphere, which means you really want to start at like maybe 1 kilometer. And then once you get up to 40 kilometers, you can throw off the fairing. So then what we do is we push our way out here to min-miss, make a slight inclination change, make a slight adjustment, try and get that as absolutely close as possible before decoupling the injection stage. Once we do that, then we deploy that satellite using infernal robotics to move those arms down, just extend the solar panels and the radiators that come from Interstellar Pack, and then we're on our way. Now, if you do not get your periapsis, your expected periapsis, as close as possible to the planet, you may end up not having enough fuel. So I use my little node adjuster there to get as close as I can. And then once we do, I'm going to show you here. You can see I'm going to put in the total amount of fuel that I have, which was minus 180 and for a retrograde. Notice that would actually crash me. So I had plenty. I can push that back out again and see we only needed 157. The trial and error method goes like this. We know that we need the 160 in the payload, and we have that. So we're just going to completely ignore this. We're going to count how much is in the lower stages that we're about to add. We need to start adding stages. Because I'm using deadly reentry in Ferrum Aerospace, I'm going to have to put a fairing on here. The next step is I want to put on some fuel and take a guess at the engine. Now, most likely I'm going to have to use 2 stages for this because there's just no way that I'm going to be able to put enough fuel on one small engine in order to get it to go up. Either that or I could do side boosters, perhaps. Let's first look at trying to do it with an engine. I have one that I really like here because it has a 400 ISP in a vacuum from the KW rocketry pack. It's very useful for being in orbit. So let's just see how much we can get on that while still being at a 1.0 or better thrust to weight ratio, which I will look at up here in my MechJeb window. The first thing you do is put the absolute smallest tank you feel like you could possibly get away with, and then the engine that you're interested in. And notice it says 2.64. So I actually could go way, way higher on that. Now, I'm not going to really launch this with all these little tanks, but what putting multiples lets me do is find where that 1.0 actually kicks in. So I'll just keep adding these tanks over and over again until that thing drops down to 1.0. We're down to 1.5. I can maybe take a little stack of 3 here, put that on, and you keep doing that, 1.6, and so on. We'll go a little further, 1.08. Okay, that's close enough. So if I wanted to, I could have this be my upper stage. It looks a little bit long, but it does have 3572. Actually, that right there is going to be this stage. So it's a 1.12. That's pretty decent. It has a 3573. We need the 4000. So, and I want 100 or 200 extra because that's what you need in order to account for the atmosphere. Notice if I was using this engine, it's 350 at absolute sea level. It's only 400 in a vacuum. So I would have to account for the lower 1,000 or 2,000 meters where the engines are less efficient. Most of the time you will be in the vacuum efficiency, but on a launch, you still need to account for that sea level inefficiency of the engines. So if I want to make this rocket a slightly more reasonable size, because I know I have plenty on there, maybe we could go for something roughly about that length. So now I go over here and I find something that looks like it's the right length. That's pretty close. What I could do is I could take that off, put that on, and then get a small tank. Either put it there or just because it might look cooler, I could put it at the top. Either way, it doesn't really matter. So there we can see we have a 1.26 thrust to weight, which is really good, especially for orbital injection, and a 3290, almost 3300. So the lower stage that we want to add is going to need to have 1500 delta V in it. So let's see what we can put on that might match up with 1500. Most likely this is still not going to be a large enough engine, but we'll take a look. Once again, you take a small amount of fuel and put the engine on just to get an idea of where you're starting. And we know we want that to be 1500. It's only 300. Of course, I didn't expect it to be high enough yet but this also lets me watch as my thrust to weight ratio is going to drop. So I'm going to start duplicating this fuel tank like I did with the other one, just to get an idea of how much we need. So we're still doing okay. I'm going to duplicate it even further. It's starting to become a very long rocket. I might want to look into having something on the side, although we are now really close to this. So chances are, if I could get the same amount of fuel that you see right here and put it in as less fuel tanks specifically, still use that engine, we might be able to lift off with the amount that I'm looking for, because I only want 1500. We're really close right now. And there we go, we have it. We have 1500 here, we have 3290 up there. That's a thrust to weight that's not too bad in Ferrum Aerospace with a 1.7. I usually like to go a little bit higher than that. I'm kind of concerned that I'll be down in the lower atmosphere for just a little bit too long. It would have been nice to get a slight boost on that. If I wanted to get a slight boost in just the thrust to weight ratio, what I could do is use a couple small, very small radial boosters. So we'll grab some decouplers and stick those on the side. And there, now it is plenty big. It has a 2.1 thrust to weight lifting off, which is going to be fantastic. Then once we decouple, we have enough fuel in here in these 3 stages to hit that amount that we were looking for. So this rocket is ready to go to Minmus. If you watched the math section and you saw the rocket launch there, you can actually just end the video right here, because the rest of this is the exact same but with a different rocket as what you already saw. This is for the people who didn't see that part. You can see here, because I'm using Ferrum Aerospace, I took a nice low 1,000 kilometer gravity turn, and now we're trying to get that apoapsis as close as we possibly can to Minmus. So I'm using a little node manipulator here that lets me fine-tune my node to be as close as it can be. That way when we decouple that injection stage right there and start deploying the solar panel using Infernal Robotics for those arms and for those right there, and then we'll put out our radiators from the Interstellar pack. When we get there, we will be able to use as little fuel as we can out of the actual satellite itself. And you can see here, I'm circularizing where it's only going to cost me a little bit less than what I actually went with. So that's plenty of fuel left over. Thanks, Kerbonauts. I'll see you later. Good luck out there.